All right, so this is the video lecture for Chapter 4, Objective 4, AP Calc BC. And what we're going to be looking at are two fundamental theorems of calculus, so the first one and the second, in addition to like a couple other things. But that's like the main kind of focus of this. So the first thing we want to talk about is continuity. So one of the things that we have, like when we have a derivative, like we have to kind of be careful about like, hey, can we differentiate here or not? And so we are restricted by differentiability with more than just continuity, right? So if we have a linear absolute value graph, for example, and let's call that C, and we'll just say this is A and this is B. Like this graph is continuous, right, from A to B, but it is not differentiable at C because of the sharp turn. So we had like kind of two things that we had to look at is not only did the function have to be continuous, but it could not have that sharp turn. Otherwise, it's not differentiable. Well, integration is a little bit different. It doesn't have that sharp turn restriction that differentiability does. So as long as your function is continuous, then that means you can integrate it. It would be integrable. So if we have a continuous function, then it is integrable. So although this is not differentiable at C, we can integrate it from A to B. Okay, so just a little different there. All right, so let's talk about the fundamental theorem of calculus. So initially we'll just talk about like, like the notation component, and then we'll talk about what it means. So if we have a continuous function from A to B, and the notation that we're going to refer to is if we have capital F. So capital F means we did the antiderivative. So that would be like your power rule or the 6 trig rules that we worked with on Objective 1. Then this is what we're going to have. So we have this. So this is the fundamental theorem of calculus. Like that's a big deal. Fundamental, big deal. So we have what we call here a definite integral. So if we have A and B on that integral sign, then we have what we call a definite integral. And how we solve this type of problem is we first find the antiderivative using the rules from Objective 1. So that would either be power rule or the 6 trig functions that we know. And then so once we find the antiderivative, we don't need the integral and the dx symbol because we did that already. So we switch the notation. So we don't need to say with respect to x anymore, and we don't need to have the integration sign. So we change that notation to bracketed format, and we move the limits, those numbers there, to the right-hand side. And then once we change that notation and we've done power rule, then we evaluate our antiderivative. So evaluate it, meaning we're going to replace x with both b and a and find the difference of them. Okay, so that's how we do that. And then just one thing for notation, just to kind of make sure. There's like another way to write this notation. And so that could be where once you do the antiderivative, you can just put a single line on the right-hand side with the limits. Okay, so instead of like kind of boxing it off, you can write it that way as well. Okay, so again, that would be working with what we call a definite integral. So if there's limits, and A is what we call our lower limit, and B is what we call our upper limit. And then just because it's the upper limit doesn't mean it's the largest number. So keep that in mind. Most of the time it will be, but it doesn't have to be. And then just a reminder, it was called an indefinite integral of what we did in Objective 1. And our answer here came out as some sort of function, right? So the answer here would be some sort of function of x. Whereas on this one, it will be a numerical value, right? Because we're evaluating our function meaning we're going to substitute numbers in. So our final answer we get out will be a numerical value. All right, so we're going to take a look at what it means, like what are we looking for? So we're going to find the answer using geometry, and then we'll apply the calculus concept to see if we can get the same answer. So provided I don't make an arithmetic mistake, we should get the same answer. Okay, so first we're going to start with like what it is we're even talking about. Okay, so I'm going to just do that off to the side over here. And so we have, so this is just like off to the far right. So if I have this integral from 1 to 4, and the derivative I'm working with is x minus 4 dx, right? So that's my derivative. So let's go ahead and graph that. So I'm going to just take this guy right here, and I'm going to write it as a function. So just y equals x minus 4. And we're going to graph it from 1 to 4. Okay, so the 1 to 4 because of that right there. So let's take a look at that graph. So when x is 0, y would be negative 4. And then when I have a slope of 1, so it's going to be symmetrical, so that means it'll cross over here at 4 as well. So negative 4 and 4 would be my two intercepts. So I'm just going to draw that. And it's linear, so pretend that's a straight line. And then I'm only going, though, from 1 to 4. So here's x is equal to 1. And then I didn't do this on graph paper, but that ordered pair, so when x is 1, that would be 1 comma negative 3. And then over here, that would be at x equals 4. So I'm looking from 1 to 4. So what this is referring to is it is asking, or what it gives us, is it gives us the area of the space that's between the x-axis, the function, and bounded by these limits. So meaning if we look from 1 to 4, and I look at the space that is between the function and the x-axis, so the space right here, then if I apply calculus to this, it would tell me how large that area is, which is not impressive at all if it's just a triangle, right? Because we'd be like, well, 1/2 base times height, like, do I really need to do calculus to figure that out? And no, you don't. But if you're given functions like the square root of x, like, what's that formula? Interesting, right? Okay. So here, so I know what the area of that triangle is. That is 1/2 base times height. So the base would be from 1 to 4, which would be 3. And then the height here would be 3 as well. But what's different is it's directional, meaning that if it's above the x-axis, it would be one thing, and if it was below, it would be another. So in this case, it's below the x-axis, so that means the direction is negative. So I would actually say my height is negative 3. And so the directional area, so the area itself would be 9/2, but the directional area would be negative because it is below the x-axis. So hopefully when I go and apply calculus to this problem I'm about ready to do, I get a value of negative 9/2. So what this is finding us again is kind of, sometimes it will be displacement because you'll have stuff above, stuff below. But what we're looking at in general is kind of that kind of contained area. All right, so let's see if we get that answer, negative 9/2, without graphing it or using geometry formulas. All right, so we're just going to do our steps off to the side here. So the first thing we want to do is just find the antiderivative. So we're going to be applying our 4.1, right? So apply your 4.1 knowledge, so power rule, and find the antiderivative. And it could be also not just power rule, but it could be your trig rules as well. So you're applying your 4.1 knowledge, and we're going to be finding the antiderivative, making sure that you're doing your notation appropriately as well. All right, so for right here, this would be x to the power of 1. So I would add 1 to the new, add 1 to the power, so that would be 2, and then divide by the new power. And then minus, and then the integral of 4, that would be like 4x to the 0, so that would be 4x to the power of 1 divided by 1. So we found the antiderivative, and then we're going to switch notation, right? So I just integrated with respect to x. And so now I'm going to switch notation, bracket it off, and then move the limits to the right, so 1 and 4. And then once we do that, our second step is to substitute the limits in. And when we do that, we're going to do the difference, right? So we're going to, in particular, we're going to substitute in the upper limit, which is going to be 4. And then we're going to subtract, and then substitute in the lower limit, which is 1, right? So in particular, we're doing an order, right? So it's not just willy-nilly. So we're going to evaluate this function over here with 4. So replace x with 4. And then now I have to do the same thing again, and I'm going to substitute in 1. So 1 squared over 2, and then minus 4 times 1. So what did I do? I substituted 4 into both of those functions. That's what I did right here. And then minus, because it's f of b minus, and then substitute in 1. And then we're going to do the arithmetic, and again, we're hoping to get negative 9/2. So that would be 16 divided by 2, which is 8, and then 4 times 4 is 16. And then 1/2 minus 4, so like that. And then this would give me negative 8 here. And I'm going to go ahead and, what am I going to do? I'm going to distribute the negative. Let's do that. Okay. And then negative times negative, so that'd be positive 4. Just to kind of make that a little easier for me. And then negative 8 plus 4, I'm going to add those together. So that would give me negative 4. And then minus 1/2, which is negative 4.5, which is also negative 9/2. So ta-da. So, like, what's cool about that? Like, all kinds of things cool about that. So finding the area of a triangle, easy peasy. But how do I find the area of something that involves a square root or a quadratic? Well, you know how you do it? You use the fundamental theorem of calculus. All right, so let's go ahead and do a couple more. Okay, so a couple more. All right, so the first thing we want to do, right, is we want to find the antiderivative. So I'm going to do a little rewrite here. So this is divided by 2, right? That's just a coefficient. So I'm going to rewrite that. So that would be 1 over 3, or 1 to 3, excuse me. That would be 1/2. All right, that's the same thing. I didn't do anything fancy here. So now remember from your 4.1 is that if it is a numerical value, a scalar, a coefficient, that can pull to the front. Now if there was a variable on that, it would have to stay where it's at, but there's not, so I'm just going to take that 1/2 out to the front so I don't have to, think about it, and then leave my polynomial after the integration. Okay, so that 1/2, I'm just kind of moving out to the front, and I can do that because it's a number. If that was like a 1/2 x, I could not do that. All right, so now we're going to go ahead and find the antiderivative. So we're going to do power rule. And when I do that, I want to make sure I always switch notation to say I'm done with the antiderivative. So we're going to add 1 to the power, so 2 plus 1 would be 3, and then divide by the new power. And then I'm going to do the same thing on x to the first. So add 1 to the power, so 1 plus 1 is 2, and then divide by the new power. And then my lower limit is 1, my upper limit is 3. And then I'm going to simplify this just a little bit. So I've got the 3 divided by 3 would be 1. And then this would be 5/2. And then from 1 to 3. Okay. And then we're going to substitute the upper limit in first, which is 3. And then minus, substitute in the 1, so that would be 1 cubed times, or plus 5/2 times 1 squared. And then all of that, we're going to take half of all of that, right? Okay, so let's go ahead and we'll do this just a little bit, like you don't have to do all of this, so we'll just do some of this. So 3 cubed is 27, and then this would be 3 squared, which is 9, times 5, 45 over 2, and then minus, and then 1 cubed is 1, plus 5/2, and then we would take half of all of that, okay? And then you can go through and do the arithmetic on this, okay, with, by hand or with your calculators if you wanted to, but just in general, like I would be subtracting these two here, right? So 45 minus 5/2, because those are like terms, so that'd be 40/2, which is 20. And then 27 minus 1 would be 26, so I would have, 46 and half of 46, so 23. Yeah, maybe. So check my arithmetic. Hopefully that was right. All right. So let's go ahead and do one more. And then if you're feeling pretty good, you might want to press pause and try C, and then forward and see if you got the same answer as I did. All right, so square root of x, so I'm going to go ahead and do a little rewrite. So that would be x to the power of 1/2, and then plus 2. And then I want to do power rule. So I'm going to add 1 to the power, so that would be just the same as adding 2 over 2. So that would be x to the 3/2. And then divided by 3/2 is the same as multiplying by 2/3. And then the integral of just 2, x to the 0, would be 2x to the first divided by 1. Change your notation, and then your limits are from 4 to 9. And then from there, we would evaluate this at 9 and then 4 and find the difference. So this would be 2/3 and then 9 to the 3/2 plus 2 times 9. So that's substituting in 9. And then now I'm going to go and substitute in 4 and then subtract that value. So this would be 2/3 and then 4 to the 3/2 and then plus 2 times 4. And then from there, I would go ahead and do that arithmetic. So now keep in mind that if we have 9 to the 3/2, this means square root of 9, right? So this would be the square root of 9, which is 3, and then cubed, which is 27. And then 2 times 9 is 18. And then there's a 2/3 again. And then again, square root of 4, which is 2, and then cubed, which is 8. And then 2 times 4 is 8. And then I'm going to simplify that. So that would be 3 into 27 is 9. So 9 times 2 is 18. And then that would be 16/3 plus 8. And then what do I have? 36 here minus 8. So that would be what, 28? Minus 16/3. And then that would be 84. What's 84 minus 16? 84 minus 16, which is something 22 1/3? Yeah, maybe. I should probably have a calculator handy, or hopefully that's right. Okay, something like that. All right, so hopefully that math was good. All right, let's go ahead and take a look at the page 2 here. All right, so for page 2, we're going to take a look at the other fundamental theorem of calculus that we're going to be working with, and this is called the second fundamental theorem of calculus. And this one, what it is referring to is kind of that relationship of the inverse operation of differentiability and integrability. So can we take a derivative and integrate? How does that work if we have a definite integral, right? If we have function, you know, either both of these are functions or one of them is a function. So like, how do they work? So we already talked about how a derivative and an integral are inverses, like, right? So if they're inverses, they undo each other. But then it's like, well, what happens then to the limits h and g? So what do we do with that? So essentially what's happening is there is no antiderivative that we're finding, right? Because the derivative and the integral will cancel each other out. So this won't change, but we have to apply these values here. And how we apply them is we still evaluate. So we're still going to evaluate f at g and at h, but we have to take into account that chain rule piece. So we take the derivative of g and the derivative of h, and we multiply those in. So that's what second fundamental theorem of calculus is saying. Okay, so just to kind of be clear on that. So this is just off to the side here. So if I have the derivative here, and the integral, and I'm just going to do a and b. So a and b do not have to be numerical values. They can be like variable expressions, which they will be. So if I do one thing at a time here, right? So if I integrate, right? So that would be bracket capital F, and then from a to b, right? So that's just the integral notation from lowercase to uppercase. And then we would evaluate at a and b. And then now if I have to take the derivative, right, I'm just going to go backwards and just redo everything, right? So this derivative, a capital F, so if I take the derivative now, capital F turns to lowercase f. But I have chain rule, so the derivative of b would be b prime, right? Because you take the derivative of the outside and then multiply by the derivative of what's inside. And then the same here. So the derivative of the outside would be lowercase f, leave the inside alone, and then times the derivative of what's inside. Now, if a and b were both numbers, then this would just equal 0, right? But they're not going to be, so we'll take a look at that. All right, so a little confusing, but let's see if we can pull that together. All right, so for example 2, they want us to use the second fundamental theorem of calculus to find capital F prime. So here's capital F. So they're asking me to take the derivative, right? So they're asking me to take the derivative with respect to x of kind of that whole thing. So capital D, so capital F, its derivative would be capital F prime or lowercase f, like however you want to write that. And so what it says is the derivative is going to cancel the integral. So this is not going to change here, but we have to do something with my limits. So what we do is we take those limits and evaluate it. Okay, so we're going to take 3x and substitute that in. So that's still going to be the square root of 3x to the power of 4 plus 1, but then times g prime, right? So we're following this up here. So times g prime. So the derivative of 3x is 3, so then times 3. And now minus, now we're going to evaluate h of x, so now we're going to substitute in the lower limit of -1. So that would be -1 to the 4th plus 1. And then times the derivative of h prime. So the derivative of -1 is 0. And so then my answer would be f prime of x is equal to 3. I'm going to put that 3 in the front. And then 3x to the 4th would be 81x to the 4th plus 1, and then minus 0. Okay, let's take a look at b. So same thing again. So we want to find the derivative. So when we take the derivative of f of x, that will turn into f prime of x. The derivative will cancel the integral, right, because they're inverses. And then we evaluate the 5, so that would be cosine of 5 cubed, and then times the derivative of 5, which is 0. And now minus evaluate by substituting x squared in, so that would be cosine of x squared cubed, which would be x to the 6th, and then times the derivative of x squared, which would be 2x. So that would be 0. So then I would have 0 minus, and then I'm going to pull that 2x to the front, cosine of x to the 6th. Okay? All right, so there's the second fundamental. So that can be confusing sometimes, but that's that one. All right, and then the last one here. Okay, so mean value theorem for integrals. So we had mean value theorem for derivatives, so make sure you don't get those two things confused. All right, so this is specific for integrals, and we'll have application problems of these here. I forget what lesson, but we do have some application problems that we do with this a little bit. All right, so if we have a function that is continuous on the closed interval from a to b, there's some number out there on that interval where the integration component, so the definite integral, is equal to f of c times b minus a. And this is one of the important pieces of the whole thing that we're saying, is where f of c is our average value, and it is just equal to this. So this is really the main formula that we work with, because most of the time they're going to ask you for that average value. So in that case, this is really what we would be working with all the time. And so these are just the same, as just f of c is isolated, right? So how do you isolate f of c? Like that was just by dividing that b minus a over, and that's where that formula came from. Okay? And then we'll talk about graphically like what that's representing as well, so that hopefully it might make sense of that. Okay? All right, so let's go ahead and start with this problem here. So for this example, they're asking us to find the average value. So the first thing that we want to do is like set up and use our formula, right? So we're going to go ahead and just use our formula. So So we're going to set up that formula. So this guy right here. And then when I do that, I'm going to do a little rewrite here so that I can integrate this easier. So I would have f of c is equal to the integral from a to b. So our a is going to be our 1, and our b is going to equal 3. So we're going to have the integral from 1 to 3 of f of x. So again, I'm going to do a little rewrite and pull that up to the top. So that would be 9x to the negative 3, and then dx, and then all divided by b minus a. So all of that is divided by b minus a, so 3 minus 1. And then now you're going to go ahead and apply the first fundamental theorem of calculus. So I'm going to abbreviate that FTC, meaning you're going to use power rule to integrate and then evaluate that with 3 and 1 and then simplify. Okay, so we've got, so power rule, we're going to do power rule here. So that would be 9x and then add 1, so that would be negative 2 divided by negative 2, the new power. And then switch notation and then move the limits to the right, 1 to 3. And then all divided by 2. 3 minus 1 is 2. Okay. And so let me clean that up. So this is, so I'm going to move that divide by 2 up, so that'd be like a 1/2. And then I'm going to rewrite this just to kind of help me see that a little bit better. So this is 9 over 2, so that's negative 9/2. And then 1 over x squared, and then from 1 to 3. So all I did was kind of clean this up a little bit. So instead of dividing by 2, I wrote it as a multiply by 1/2. And then the negative 9/2, I just moved it as its own coefficient. And then with the negative power, I dropped it to the denominator. And so then now from here, I'm going to go ahead and substitute in the 3 and the 1. So I have these two numbers here, so let's multiply that together. So it doesn't matter that it's like bracketed with the 1 and the 3 because there's no x here to substitute in. So that's why I can combine those. So then that would give me negative 9/4. And then now I'm going to go ahead and evaluate the 3. So that would be 1 over 3 squared. And then evaluate in the 1. 1 squared is 1. So again, no variable here, that's why I just moved it all to the front. So negative 9 over 4, and then that would be 1/9 minus 1. So I would have negative 9/4, and then 1/9 minus 1, so that would be 9 over 9, so negative 8/9. So that would reduce, so then I would have that equaling 2. All right, and then from there, I'm going to go ahead and do, and that's my answer, so sorry. So there's my average value, okay? So the average value is equal to 2, and so now for part B, it's asking me to find the values of C guaranteed by the mean value theorem for integrals. So what I do here is I take that average value and I equal it to f of C, right? So my average value, which is 2. Let me move this around, sorry. So this is kind of like step 3 because this is kind of a continuation of part A. So now we're going to set the average value, which is the number you just got, equal to your function. So my function, so that would be up here, so 9 over x cubed. And then equal that to 2. And then just solve for x. So I'm going to multiply the x cubed over to the other side so I can get it out of the denominator. And then divide by 2. And then cube root. And so then x would equal the cube root of 9/2, and whatever that is. And then that's the end of that.